From Diamond Light Source, this is the Diamond Podcast.
This month, we go in situ at the light source to discover how scientists are visualising experiments as they happen.
You need to, just like a 3D movie, see what's happening in 3 dimensions. You also need to then see how things change with time, and that's both the chemistry and the morphology. We apply this to things from aero engines to bioactive glasses used for implants. The application's only going to expand and expand exponentially.
Manchester University's Peter Lee explains the benefits of experimenting dynamically as we explore how synthetic implants are being improved to last longer in the body, how catalysts are being monitored in action to improve their efficiency, and how aeronautical engineering is being revolutionised with 3D printing. All that, plus the latest news from the synchrotron, including new insight into preserving our ancient buildings, coming up on this March edition of the Diamond Light Source podcast.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
When analysing materials, processes and chemical reactions, it's difficult to learn much from merely the end result or starting point of your experiments. The ability to monitor an experiment as it happens, or in situ, can be invaluable to get a clear understanding of what's going on. Claire Pizzey, Diamond Industrial Liaison Officer, explains more.
Well, many experiments come about because you're interested in knowing what happens to your sample while you do something to it. So in situ means looking at a sample under realistic conditions. So you might have a situation where you know a sample, your system does something interesting while you apply some kind of external stimulus, which could be heating or cooling or putting it under pressure or stretching it or whatever it is that's interesting, and looking at the changes that happen. And experiments that cover those kind of systems, like while you're doing something to, are called in situ experiments.
So it's really kind of seeing things in action and seeing this entire process rather than, as you said, just seeing the beginning and the end of a process.
Absolutely. And previously what we've had to do is take a sample beforehand and look at it. Then we've maybe taken it away to a lab somewhere else. We've processed it for 6 months, waited for something to happen, whatever it is that's important. And then people come back again and measure the sample again. But what's always better is if you can measure it before, change it, measure it while you're changing it, and then measure it at the end. So you can monitor all the stages through and understand how it gets from A to B, because it doesn't always go the way you think.
And what would you say are the main benefits of this? I mean, it's obviously great to see things in action, but what would the kind of key benefits be?
Well, there are a lot of areas so that it can be used for. I mean, it's hard to pin those down to just a few, but for example, in catalysis, some of the chemical reactions that happen in processes that are used to manufacture things that everyone has in their house involve catalysis. Now, what we know is that we need very good catalysts that are energy efficient, and they need to be selective, so they need to just help you produce the thing you want to produce, not the byproducts. So there's a lot of work that goes into designing catalysts. But a lot of these reactions occur at high temperature. They occur when you've got different mixtures of gases running through. So if you looked at the catalyst when it was cold in a normal air atmosphere before, then you do the reaction, and then you look at the catalyst when you've taken out afterwards, again, when it's at room temperature and in a room atmosphere. It may not look as different as it might do at 800 degrees with hydrogen flowing across it, or a nitrogen gas mixture, or whatever is the important gas mixture for that particular reaction. So it's really important to understand, in a chemical process, to understand the chemistry that's happening under those conditions.
And I mean, so that was a chemical example, but as you said, this is useful across a wide range of sciences. In particular, I would say the physical perhaps more than the life sciences.
I think so. I think it's important to say that when you're looking at protein crystals, proteins are not crystalline in the body, so we infer things from that, and it's challenging to do those experiments, and we can't do those in situ. But in terms of the physical sciences experiments, I think it's a significant portion of experiments that are done that are really looking at changing the conditions the sample experiences during the experiment. So that could be heating it or cooling it or stretching it, applying some kind of mechanical strain. So I talked about spectroscopy experiments where we can look at the chemistry of the system, and we have a microreactor system that will control the temperature and gas flows and things. But we also have a range of what we call sample environments here at Diamond, different for each of the beamlines, that can be used to recreate different conditions. That could be like our tomography stage on our engineering beamline, so you can look at rotating your sample while you're imaging it, so you can really see through and into your sample. Or it could be looking at how the structure changes while you're stretching something or you're applying an electric field. But it's very important for the physical sciences.
So this is possible across quite a range of the beamlines here at Diamond, but you do actually have a few specific ones. One in particular is called the Extreme Conditions beamline.
Exactly. So the Extreme Conditions beamline has been designed so that you can recreate the conditions inside a volcano in terms of pressure and temperature. And that's interesting because we're looking at changes that happen in samples, but they only happen when they're under those extreme conditions. So that is, let's say, an extreme version of In-Situ, but many of the other instruments that we have here at Diamond, or the different beamlines, have different sample environments that create this. So some have cryostats, so they can take temperatures down very low. Some have furnaces, so we can take temperatures up very high. And the other important thing is to say is that many of our users bring their own equipment, which can be installed on the beamlines and recreate whatever it is that's special about their sample.
So a wide range of applications. That was Diamond's Industrial Liaison Officer, Claire Pizzey. Now, as Claire mentioned, in-situ experiments tend mainly to benefit the physical sciences field over the life sciences. But Maurice Collins from the University of Limerick is working on a range of materials that have biological benefits, orthopaedic implants. And Maurice is determined to find the best material to get these implants lasting as long as possible inside the human body.
The material that we use is called ultra-high molecular weight polyethylene. This is a polymeric material, and it's widely used in artificial joints, where it provides a bearing surface between a hard metal and ceramic component.
So how widely would you say these are used, and what are their real kind of benefits? Why are they used so commonly for this purpose?
These materials are used commonly because they have a high molecular weight. So that gives it very good creep resistance, which means that they have very good mechanical properties under stress and strain.
And how do they compare, say, to what was previously used? So what was previously used for these types of implants, and how has this improved upon, I guess, those previous properties?
Previously used materials were metals on metal, and these materials wore very quickly, and there was lots of complications for the patients. These new ultra-high molecular weight polyethylene materials have a lower wear, so they have slower, better wear resistance.
And I guess what are you really looking into, though, with these materials? Because although they are quite widely used in implants, there's still, I guess, quite a lot that's not quite known about them.
Yes, there's a lot of structure-property relationships that are not known. These materials have problems when they're sterilised. During the sterilisation process, they have a tendency to become stiffer and become brittle. When companies process the materials before they're implanted into the patient, they have to undergo sterilisation, and the sterilisation changes the properties of the material.
Ideally, you don't want something brittle going into the body, do you?
Exactly, you don't. This shortens the lifetime of the implant, and ultimately you would require revision surgery and a new implant.
Are you really looking into what happens during the sterilisation process to cause them to become brittle?
Exactly. We're looking at what happens during the sterilisation process, and we're using the facilities at Diamond to be able to predict what happens and to be able to prolong the lifetime of these materials. And
I guess this is where kind of the science that's possible at Diamond really comes into its own, because you can actually study this in situ, essentially, so whilst the sterilisation is going on.
Exactly. We pre-sterilise the materials in different atmospheres. We sterilise them in oxygen and in nitrogen, and we also do a heat treatment. And once they're sterilised, we then put them into the rig at Diamond, and we can measure the strain as a function of crystallographic change in the rig at Diamond. So what we can learn from that is we can measure phenomenon down to sub-nano, down to 10 to the minus 12, so very tiny feature changes in the material as we strain it. So we can see the effect of different different sterilisation conditions and what that does to the nanostructure of the material. And then we can relate this back to the wear resistance of the material.
And then would the aim here then be to see which of the different processes is the best in terms of not resulting in a brittle material?
That's exactly it, yes. We would then be able to identify how the annealing restores crystal perfection and how it ultimately improves the performance of the implant. And this gives us a much greater understanding of how we can produce stable implant-grade polyethylenes, so stable materials while they're in the body.
And what have you managed to see so far?
We managed to get a set conditions which gives the best lifetime conditions for the material. So we're able to optimize the sterilization process, and we have seen that heat treatment performs a key role during this process.
So it's a combination of heat at certain temperatures and certain conditions that are going to give you the best material?
Yes, yeah.
So what would be the next stages here? So you've identified which one leads to the least kind of brittle material at the end of it all. And so this would ideally then be the one commonly adopted for actual implants in the future.
That's correct, yes.
How important would you say the fact that you've been able to do this kind of with the processes going on? So compared to what was possible in the past, how much of a difference has it made to be able to do things like this in situ?
Well, before you could only guess. You could only get ideas of how crystalline a material is. So you could measure how hard it is. But now, using the equipment at Diamond, we can actually get numbers on the size of the crystallites, and we can predict mechanisms as to why this is occurring, which was impossible to do before.
What would be the next stages then in order to really, I guess, get the best material out there for use in the implants?
Well, the next stages that we're looking at are to produce materials where we can mould the material. Currently, manufacturers, they produce the materials by an extrusion process and then a machining process. Because the molecular weight is so high, it's difficult to mould the material. So we want to produce a blend of two different polymers so that we can make a material that's mouldable. And then we want to be able to take this material to Diamond and measure the same set of conditions that we measured before and see if we can get the optimum conditions for this new mouldable material. The new mouldable material would offer many advantages, such as quicker processing times and lower cost of production.
So ideally a kind of a mouldable material to mould implants in the future, which then also, once sterilised, don't become brittle.
Exactly, yeah.
Maurice Collins from the University of Limerick.
Did you know that Diamond's floor-level monitor system shows Diamond tilting twice a day due to the moon passing overhead?
This is the Diamond Light Source podcast, and this month we're going in situ to see experiments in action at the synchrotron. Still to come, we hear how materials made with 3D printers are being improved by dynamic monitoring of their production, and we bring you some flash fiction from Diamond's light reading anthology. But first, good news for the construction industry, as Mary Cruz, Diamond's communications officer, explains with this month's Diamond News Update. Mary?
Yeah, we've got lots of great stories coming out of Diamond at the moment, a couple in particular about the construction industry. So scientists from the University of Cardiff have discovered that hair particles in modern plaster could compromise the stability and safety of our modern buildings.
So hair particles, I didn't realise these were in our plaster.
Yeah, well, hair plaster's been used in building materials for thousands and thousands of years. The little hairs help to bind the plaster together and work to control any cracks that might appear in the mortar as it dries or flexes over time. In the UK, we generally stick to horsehair or cow hair, but most types of hair provide strengthening properties.
And so have the sources of this hair changed over time, or do we still get them from horses?
No, yeah. Traditionally, builders would source their hair from the pony down the road. However, nothing is that simple in a globalised age. So these days, we actually import our hair from around the world, most often from Asia. But modern doesn't always equal better. The team of scientists who carried out experiments at Diamond have discovered that these new imported hairs could be bad news for the stability of our buildings.
So how do they know this? What have they seen as the problem?
Electron microscopes were used to view voids left in the limestone of a structurally compromised building. The scientists found that the building material was weakened because the modern hair particles inside the plaster had dissolved, leaving cracks inside. So the scientists looked at two samples, one from a 200-year-old chalk lime mortar and the other from a modern building. And they found that the hair in the modern building was coarse and brittle, much more so than the soft, flexible sample found in the old stone.
And so this is quite a big difference. Why do they differ? What's really causing this?
Well, the difference between the old hair and the new hair is that modern commercially available hairs are generally treated with oxidizing agents such as bleach or acid prior to sale. Spectroscopy experiments on Diamond's I-22 beamline have revealed that imported horsehair contains high levels of cystic acid, which isn't found in fresh, untreated hair. What's more, small-angle X-ray scattering experiments have confirmed that this treatment leads to the loss of keratin structure in the hair. So what this means is that because of its acidic properties, imported hair often dissolves inside the plaster, and as a result, over time, vacuums form where the hair once was, causing little tiny cracks in the plaster. And these cracks can go on to cause huge industrial failure, and the buildings can become dangerous and completely uninhabitable.
So I take it that this is the ideal would be to overcome this in the future.
Yeah, well, by identifying the problems caused by treating hair with these oxidizing agents, these scientists are helping to create the materials and the architecture of the future.
And, well, staying on the topic of buildings, but now moving on to the preservation of our more cultural buildings. There's been some findings here too.
Yeah, Diamond scientists are helping to protect our buildings, and here we look at conserving our historic buildings and protecting our cultural heritage. So it's another construction-related story here, and we're moving from hair to olive oil. Perhaps not the most obvious of building materials, but a team of scientists have discovered that a combination of oleic acid and a Teflon-like material could be just the trick to preserving Britain's historic limestone building.
So why is such preservation needed? What's the problem with the buildings today?
Well, in the UK and most of Europe, in fact, we're famous for beautiful works of historic architecture. But unfortunately, a lot of these beautiful structures are starting to show their age. Discoloration and erosion of the intricate carvings and gargoyles that characterise our medieval architecture. Now, that's because of pesky environmental pollutants like acid rain. And what's interesting about limestone buildings is that they have a memory. So all of those years of industrial smoke and smog are locked up inside the stonework, destroying the material from the inside. And this means that past attempts to coat these buildings in hydrophobic substances, that is, those that repel water, have found that they lock inside all of that nasty pollution and prevent the building from breathing. And this causes the condition of the building to actually worsen rather than improve.
And how are scientists then trying to overcome this with this new material?
Well, the findings made on Diamond's B18 beamline are so important because the team, led by Dr. Karen Wilson, has discovered a material that both repels water and allows the building to breathe, getting rid of all those nasty locked-up pollutants. The material uses the repellent properties of oleic acid, the substance most commonly found in your everyday olive oil. The problem is you don't want to leap ahead and slather all of our beautiful architecture in olive oil only to find that it turns them bright yellow or causes them to crumble to the ground. And that's why the team used X-ray absorption analysis to examine the ways in which the new oily substance reacts with limestone. So at the moment it's still early days, but it could well be that the team has uncovered a means of preserving our historic buildings and our cultural heritage for centuries to come. And the solution was hiding in the kitchen cupboard the entire time.
So two great findings there, really. One for stronger buildings in the future and another to protect the ones that have already been built. So what else has been going on too?
There's lots more going on the beamlines. Research into nanotechnology, investigations involving magnets to develop new LED lights, studies into the structures and possible treatments for our various diseases. You can read all about the fascinating science that takes place at Diamond on our website at diamond.ac.uk.
Diamond's Communications Officer, Mary Cruz. Now, this month, we're exploring the potential of in-situ experimentation and how this new level of insight is benefiting a wide range of scientific disciplines and applications. Peter Lee, co-director of the Diamond Manchester Beamline, has used this method of analysis for a wide range of his research.
So we use in-situ experiments because you need to, just like a 3D movie, see what's happening in 3 dimensions. You also need to then see how things change with time, and that's both the chemistry and the morphology. We apply this to things from aero engines to bioactive glasses used for implants, through to how you extract efficiently mineral resources. Each of these has a huge impact on making the process more efficient, reducing CO2 emissions, and in the case of healthcare, actually reducing patient stays in hospital by up to half.
And what are the main kind of benefits of doing this all in situ? So what are the various kind of conditions that you're looking at or operating under, and why is it important to kind of look at things in action?
Well, let's take a specific example. One of the things we're looking at is called additive manufacturing. It's actually 3D printing, but it's 3D printing of metals, so you can directly make an aerospace component. We're now only making 50 or 100 of each type of plane a year. It's incredibly expensive to make it by any other way. If you can print a component, your design time's much faster. However, in doing that, it's an all-new technology which uses much faster cooling rates, very specific conditions. By looking in situ, we can actually see what's happening as it's going on, tweak the conditions, and optimize them very quickly. The second huge advantage is that we can go after we've made it and test it in situ. Things will fail. You can then see what the mechanism of failure is as it's happening. And instead of looking at the broken component at the end, see where the failure is initiated and stop it and nip it in the bud.
And I guess, why would you say that this wasn't possible before? And how's it, I guess, been made possible by the kind of new types of beamlines and designs of beamlines at places like Diamond?
It's actually been a huge effort integrating both the X-ray physics so that now you have a much higher flux of X-rays, which means you can actually take effectively radiographs or diffraction patterns in shorter times. The electronics has also advanced tremendously. So that the detectors now, instead of just a radiograph you just before saw as a shade of gray, now you can actually extract in each of the wavelengths the actual energy, and they're called energy sensitive detectors. So it's that combination, and then we've also become better at making very high precision, high accuracy, high speed machines so we can perform these experiments in situ while using these more powerful investigation tools.
And I guess focusing more on your example, say, of 3D printing and kind of printing various parts and components, could you take me through, say, a process? So something that you would like to print in a 3D way, and what you would really observe and what you have managed to see so far?
So currently, a lot of titanium components that are used inside of aircraft are cast or they're machined out of solid titanium. What we can do now is take titanium powder and run across it either a laser beam or an electron beam, and across this bed print one layer of a material. You then add more powder and then re-solidify. This is a completely different process than producing it from wrought. And because we can 3D print, now imagine a simple component such as a landing gear. In a landing gear, it's solid throughout. It turns out that the load is only really carried on the outside. When you 3D print it, it means you can make it hollow on the inside and therefore lighten the weight, meaning we're using less fuel. However, there's no way to look inside that actual final landing gear to see whether you've made it correctly. By using X-rays and tomography and the ability of the synchrotron, we can actually look inside and make sure we've manufactured it correctly and that there's no defects there. So it gives benefits both in the manufacturing and in the final inspection and testing, and then the final use.
Would you say that in situ experiments like this are just going to continue to grow then in their uses and applications in the future?
So I've worked on in situ observation for 25 years now, and it's been it was very linear growth until the last 5 years. And now with third and fourth generation synchrotron sources, it's become exponential. The number of publications in it has been doubling or tripling every year. So I think it's going to permeate through a wide range of science. We're now looking with colleagues at UCL at lithium batteries and how to actually improve and in situ observe how those are behaving to try and solve problems such as in the Dreamliner, how lithium batteries change as you change pressure and operational conditions, which you can't see in any other way. And so the applications, in my mind, are only going to expand and expand exponentially.
So watch this space in order to watch the field grow. That was Peter Lee from the University of Manchester. Now, that's almost it for this month, but before we go, we hear back from Mary Cruz as she brings us some flash fiction from an anthology created from Diamond's light reading fiction competition, which ran last year. And Mary's taking us to the brink of destruction with a piece written by Gavin Ireland.
From the outside, and indeed from the inside for all but a privileged few, the Diamond Synchrotron facility was a place for eggheads to use super powerful light for their experiments. Of the millions of experiments done there, some had resulted in advances in medicine and in practical technology, so the facility remained fairly ignored, nestled in the Oxfordshire countryside. Little did anyone know that a small group of government scientists and their plans to use the facility to see into the future were about to bring the whole world to the brink of destruction.
Mary Cruz with a tale taking us to the brink of destruction, courtesy of author Gavin Ireland. Now that is it for this month, but join us again next time for more insight into the range of science taking place at the synchrotron, as well as more news and fiction to get you thinking. In the meantime, if you have any questions about Diamond or the research taking place there, the email address is podcast@diamond.ac.uk, or you can listen to previous editions of this programme online at diamond.ac.uk/podcast or nakedscientists.com/diamond. You can also subscribe to the podcast on iTunes. Thank you this month to Claire Pizzey, Mary Cruz, Maurice Collins and Peter Lee. I'm Mira Senthilingam. Thank you for listening and goodbye.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.